month's programme, we're going to be looking behind the scenes at the UK's £360 billion space industry.
Maggie goes back to visit her old employer and makes a surprise discovery.
So what I'm holding here is the purest quartz crystal in the entire world. Who knew? And if you thought that was odd, Chris discovers some off-the-wall techniques for building spacecraft.
Oh, there we go. There we go. So that's deployed 3 meters.
From satellites that are making space safer to the next generation of space telescopes.
All that and a Sky at Night exclusive. Chris and I get to look inside the awesome new National Satellite Test Facility. What I find amazing is just the scale of this.
Welcome to the Sky at Night.
T-minus 10, 9.
When we think of space engineering, our minds generally turn to the US, possibly Russia, and these days, maybe even Japan. But if you thought you need to go to California or Star City to work in the industry, then think again. There are hundreds of companies here in the UK involved in space manufacturing. From small companies making tiny components to huge companies making whole satellites. So if you're like me and you're interested in space engineering, then you're in the right place. Stevenage has long played a part in the UK's aerospace story. Once the de Havilland Aircraft Company, this factory is now owned by Airbus. This part of Airbus is famous for 2 things: Mars rovers, which we've visited before, and satellites, which I'm off to see now. 1 in 4 of the world's communication satellites are built here. But that's only part of the story. There's actually a satellite being built as we watch. But what satellite is this?
This is biomass. It's a European Space Agency mission, one of their Earth explorers, and it is going to measure the forests of the world. In the carbon cycle, one of the key measurements that they need is how much forest is there to suck the carbon out of the atmosphere, and it's a really unknown quantity. At the minute, the only way to measure it is actually to cut down sections of forest to be able to count the amount of, to measure the amount of carbon. And so this satellite is going to have a huge radar and measure the forests of the world. The radar is able to look through the leaf cover to the trunks and the trees themselves so that it can build up a 3-dimensional picture of just how much forest there is across the world.
But I suppose that's the power of satellites. They do it all from above.
Yes, so the global view is something that you just can't get anywhere else.
So what would you say to a young person who likes space and is thinking about joining the industry?
You absolutely have to do it. There are a huge number of jobs as well. So for those people interested in science and maths, then the routes are through physics or through engineering. But there are also all the support functions around that. So we have accountants, lawyers, and administrators. And so if you have a passion for space, we need something like 50,000 more people in the space industry in the next 10 years. And so, yes, join.
I found it fun, you do. Join us.
Absolutely.
That's fantastic. Thank you so much. As you walk through the plant here, it's fascinating to see some of those skills on display as basic materials are transformed into complex spacecraft. So this is where a satellite starts its life. Now, put basically, it's just a box, but it's made up of this high-tech aluminium composite. So it's very lightweight, but incredibly strong. Now, various components are bonded onto this, like antennas and thrusters. Building a satellite is a complicated process, involving some elements you'd never imagine. One of the most surprising things I found out about this site is they actually make crystals right in here. So when I said crystals, I'm talking big crystals. This is a crystal of quartz actually manufactured here on site. It's huge and quite heavy, and quite expensive too. Now, from these large crystals, they generate these small disks. Now, they're added to the electronics and they go on board the spacecraft. So why have these pure quartz crystals on the satellites? Well, it's all about the timing. If you pass an electric current through the quartz crystal, you get a set frequency, a known frequency. Now, when you put a satellite in space, communication is very important, but the frequency of the communication can drift. These quartz crystals act as a calibration to make sure that your frequency stays on track and you can keep in contact with your satellite. To maintain that calibration, you need a quartz crystal that's incredibly pure. And the way to ensure that purity is to actually make them here on site. So what I'm holding here is the purest quartz crystal in the entire world. Who knew? The UK space industry earns £16.4 billion per year, which makes it a huge player, and which also makes it a good career choice. Saskia, Josh, you're both apprentices here at Airbus, but you're doing two different types of apprenticeships. So your engineering and your craft, so how do they vary?
I would be more office-based departments, so that could involve design for the project, could be doing testing, and that includes the materials laboratory, so be testing materials that we're going to be putting onto the satellite, and product assurance roles. So it's kind of the behind-the-scenes parts of it, whereas Josh would be more in the clean room doing hands-on work.
Yeah.
Josh, you're doing a craft apprenticeship.
Yes,
so
correct.
what does that involve in the day-to-day?
So it's far more hands-on than the engineering apprenticeship. I've actually got something I have to show you. So this is an apprentice simulation. Pipes that you see here, the way the brackets are abraded and bonded to the panel, even the panel makeup itself with the high and low density honeycomb, the edge wrapping, the harnessing, everything is the same as what it would be on a flight piece, obviously just on a much, much smaller scale. It just means that when you come off the apprenticeship, the training you've had is far more relevant to what you'll be doing in your day-to-day role.
Did you ever think you'll be working in the space industry?
No, definitely
No.
not. Definitely not.
Working in space and spacecraft is definitely not something that, I think
No.
unless you have a real passion for it, it's not something you ever think about. But then once you're here, it's very, very difficult not to be interested in astronomy, spacecraft, space hardware, and just how satellites work and why we send things to space and how they do what they do.
So it's definitely a thumbs up for apprenticeships.
100%.
I think they should be
100%.
showcased more because the academic route isn't for everyone. Going to university and sitting in lectures, I like the fact that we've had experience in the industry as well, which is valuable.
It's pushing the space industry onwards.
Yes, definitely. We're kind of the new generation of engineers.
Yeah.
Yes, and we need you. It's been fantastic speaking to young people like Saskia and Josh, who are actually working in the space industry. And it's brilliant that they're getting hands-on experience. But huge companies like Airbus are just part of the British space story. Chris has been visiting a company at the other end of the scale in more ways than one.
There's nothing much about this building that suggests it harbours space technology, but inside, Oxford Space Systems making new use of some surprising materials. Well, I've seen many strange things in satellite companies, but nothing like this. What's this machine and what is it doing?
Well, this project is about trying to integrate knitted structures into satellites and antennas, and it has to be in a metal yarn because it has to reflect the radiation.
Which makes sense, but knitting with metal sounds difficult.
It is rather difficult. We're working with this tungsten metal yarn, and as you can see here, it is very, very thin.
I can barely see it. It's like a hair or something.
And if you feel it, you can barely feel it as well. It's,
oh, wow.
Yeah,
there's nothing there.
No, it is actually thinner than hair.
Right.
Yeah. So this material, tungsten, is what we're using to make our knitted fabric.
So can I touch this? Can I pick this up?
Yeah, sure.
So it feels, I don't know what I was expecting. I think I expected it to feel like metal, and it feels soft. It feels like fabric.
It does.
If you told me I should wear this, I'd probably believe you.
Yeah, but
right?
you probably could.
Yeah, but it's made of metal. It's tungsten.
It is made of a tungsten. reason why it's so nice to touch, actually, is just because it's such a thin fiber.
What's the most challenging part? Is it the fact that this material's so light and so thin?
Yeah, I would say it is the material, because as well as this being a very, very thin material, we want it to be anti-laddering. So because it's very expensive to send it up in space, and if it's already there, you can't really take it back once it starts to get holes in it and ladder. So that's why we have to really research and test out these different structures.
And so just as a textile, it's an interesting property, and then you can use it for these satellite applications as well.
It's only when you see how dramatically these fabrics will deploy that you appreciate how important it is that they're ladder resistant. Oxford Space Systems are targeting a new generation of micro satellites, where launch space is at a premium, but which still need large antennas. And knitting is only one part of the plan, as CEO Sean Sutcliffe explains.
Well, we've got all these wonderful things here. What should we talk about first?
So let's look at this one. This stows down into something that is, that's about 5 centimeters.
Sure.
And then when it's in space, it deploys using spin energy. And of course, what you're looking for is the rigidity, the radio frequency performance, and the lightweight. Feel how light that is.
Oh, wow, yeah, that's sort of lighter than a kid's toy version.
Exactly.
Right?
So every gram is saving cost.
Right, and these are already, this sort of design's already flying.
We've got 3 of these in space already.
Okay, so what are the other things sitting on the table?
Well, let's have a look at this fabric. So this is a composite material, and you can see the mesh, which is a carbon fibre, which is to give you the reflectivity.
Right.
So this is something that is going to be solid to a high-frequency radio wave.
So you might use that for a transmitting antenna or something like that.
Exactly right. So if you take that, you can furl that up into a small shape.
Okay.
And then unfurl it.
Ha! There you go.
There we go, into an antenna.
I like the way it unfurled. If you looked at it, it looked flat, and suddenly you got this nice parabolic.
So that's, if you like, origami engineering that's giving you that.
Right.
How do you get something that's flat to unfurl out into the shape you want, which the engineers tell you need?
Yeah. So go on. Well, you said we'd leave this one till last. What I'm intrigued.
So this is a lower frequency antenna, and this also deploys.
Okay. I like that you're taking it away from me. Instantly.
I'm taking it away from you.
Yeah, very good. Oh, blimey.
There we go. So that's deployed 3 meters. I'm not the expert in this.
No, that reliably deployed. I think that's fine. Okay.
And also, look, there we go. It has that stability that we're needing as well.
Well, that was fun. I think you could.
Well,
you know, that's a good sideline for magic tricks as
yes,
well.
exactly
I think.
Right.
Across the road from Oxford Space Systems is another of the many hundreds of British organisations specialising in space engineering. This is STFC RAL Space, where, amongst other things, space-bound satellites are tested. When a satellite is launched, it's put under enormous stresses, and so it's essential to make sure that each subcomponent can survive that experience. After all, there's no bringing it back to repair it once it's been launched. Hi, Ian.
Hello.
So, vibration testing. So what's going on here?
Well, what we're trying to do here is to replicate the environment this payload will see when it's launched. So we're going to play a vibration signal into it, which provides some of the vibration it will see when it's on top of the launcher being shot into space.
And you can match the vibration to the launch vehicle, so Ariane or Indian Space Agency vehicle.
Yes, so we'll take data from the launcher manual and replicate that environment.
Now, this is sort of a fairly small component that's going to go into a satellite.
Yes, this is a small mirror assembly that's going to go into a satellite, which will be used for research purposes.
Fantastic. Well, I'm looking forward to seeing this.
This is just a calibration section. It does a number of checks to make sure that everything is responding, and now the test starts.
It's a fairly high frequency.
Yeah, 100 hertz.
I can feel it.
Yeah, you'll see the displacement is coming up a bit now.
Yes, it's blurry. Once shaken, the components are assessed for damage, passed fit for launch, or redesigned. But the launch isn't the final challenge. In flight, rocket stages are jettisoned by firing explosive bolts. and this creates shock waves. So Ian and the team have a test for that too.
The test item here is attached to a reverberant plate, and we strike the reverberant plate with this projectile. And this is fired down the compressed air cannon behind here.
So that's the bullet?
That's the bullet, yes.
So I guess we can't stay here for the actual bullet?
No.
We better go then.
Right.
Of course, it's not just the launch and the journey to space that the satellites have to survive. Once in orbit, they need to endure extreme temperatures, and all in a vacuum.
Okay, and here's Space Test Chamber 3. Okay, here it is, 5 metre diameter, 6 metre length.
I see, yes. That can take some pretty big stuff then.
Yeah, it's a 52-ton chamber. So what we're trying to do is replicate the conditions of space for the customs equipment, so spacecraft or instrument. So that is the vacuum environment, so we pump down to very low pressure, and also the thermal environment, so we can cool down to 80, 90 Kelvin or up to 400 Kelvin.
Oh, I guess because when the satellite is in direct sunlight, it gets super hot.
Exactly.
And then in the Earth's shadow.
When it's in the Earth's shadow, it gets very, very cold.
Yes. And so how do you heat and cool the chamber?
So each of these panels that you can see, the black panels, there's 46 independently controlled zones. Each panel has a liquid nitrogen feed and return and an array of heaters.
Okay.
So we can either choose to go cryogenic or we can go hot, and we can vary what's hot and what's cold.
So it's almost like as having direct sunlight. You can direct the sunlight
on one edge or the entire chamber as a uniform temperature.
And I suppose this is the precursor, so if it works here, it's much more likely to work in space.
Exactly. They're very expensive, and you want to make sure that everything's tipped up before the launch.
Yes. Well, it's an impressive facility. You probably haven't heard of most of the projects that pass through this facility. But recently, MIRI, a major part of NASA's James Webb Space Telescope, was built and tested here.
MIRI stands for Mid-Infrared Instrument. I asked its lead investigator, Julian Wright, what looking at the universe in the infrared can show us.
There's two things, I think, really. One is that it allows us to study some of the earliest galaxies that have formed, where they're so far away from us that their light has been redshifted, so it now appears as infrared light, so we measure it as infrared light with Webb, and that will allow us to understand how they formed. And it's also, infrared wavelengths are very, very good at peering through dust. So we know that stars and planets form in very dusty regions, so this is going to allow us to understand much more about how planets form in the early stages around stars, as well as looking into the atmospheres of planets and understanding some of the chemistry.
What's the first steps in actually building something like MIRI? Do you start fiddling around in the lab or what?
So some things in the instrument you've done before, some things are very new. So we started by making a prototype. So you gradually build up a little bit more knowledge about how your designs will work by building these prototypes and testing them, but they all need to be put together to make the instrument. And that putting them together to make the instrument, that happened at REL Space.
We were over at REL Space just the other day looking at the testing facilities, and I have to say, some of that looks pretty terrifying, to take something that you've worked on for so long and with such care and then subject it to vacuums and shaking and all the rest of it. Were you scared or were you pretty confident?
You can model things on computers and predict things very accurately, but there's always that little bit of uncertainty, the things that maybe you haven't quite caught. So yeah, it's scary. It's not as scary as when it's going to go up on a big rocket in a few months' time.
Well, look, I wish you all the luck in the world. We'll be watching with fingers crossed, and we'll talk to you soon. Thanks a lot.
All right, thank you.
From its position in space, the James Webb Telescope will give us unprecedented access to the wonders of the universe. But because most of us are stuck here on planet Earth, here's Pete to tell us what we can see from our own back gardens.
If you're a night sky photographer and you've taken a long exposure photograph of the stars, the chances are that you will have caught the trail caused by an Earth orbiting satellite passing through your camera's field of view. Now, whether you regard these as a nuisance or perhaps with some degree of interest, there's certainly one which is very interesting for us here in the UK. Launched on the 28th of October 1971, Prospero remains the only satellite placed into Earth orbit by a British rocket. Now, Prospero is pretty faint when it goes across the sky, but it is still there. And if you go onto one of the many satellite prediction websites available on the internet, it's possible to get a prediction for when Prospero is going to pass overhead for you. Okay, hopefully my camera is set up pointing at the right part of the sky to be able to capture Prospero's trail in a few minutes' time. Now, it's interesting that rocket launches have been known to trigger a phenomenon known as noctilucent clouds, and that's because the particulates in the rocket's exhaust create the right conditions for thin ice sheets to form in the mesosphere. Now, these form naturally as well, and for the mid-northern latitudes, they typically can be seen between late May through to early August. And these ice clouds, they occur at such a high altitude, about 50 miles up, that they're still able to reflect the sun's light, even though the sun is below the horizon. They typically appear 90 to 120 minutes after sunset low above the northwest horizon, or a similar time before sunrise low above the northeast horizon. A bright display is great to photograph, and a really bright display can be photographed quite easily with a smartphone camera, and they can be seen in urban locations, so they make great things to look out for in the summer months. Right, I'm going to concentrate on this now because Prospero is due very shortly. And there it is, a faint trail passing across my camera's field of view, and a proud moment to capture a piece of British engineering in orbit around the Earth.
Our modern way of life depends on satellites for everything from sat-navs to weather forecasts. But that technology is more fragile than you might think, and the biggest threat comes from the satellites themselves.
There are now so many useless, dead satellites in low Earth orbit that we could run out of room for new ones. Or worse, debris from crashes might make the entire space untenable. The UK arm of Japanese company Astroscale is testing an experimental satellite which comes with its very own piece of space junk, which it will lose and then learn to recapture.
So this is your test, right?
Yes,
so we
this literally will just come off here,
okay.
And we'll release that into orbit, and then the service will come along and capture it again like that. And then we're going to tumble it, and as that tumbles, we're going to maneuver the service around, because, of course, a real piece of debris will be out of control and tumbling.
And so that's the hard bit. It's sort of tracking and being able to follow the debris around.
Yeah, absolutely. I mean, no one's done that before. When you launch, say, the Progress supply vehicle for the International Space Station, they're exchanging data. You've got humans in the loop. It's very carefully controlled. But a piece of debris, there's going to be no data exchange, so the service has to do it all on its own.
I know this is a model, but you pulled that off and put it on it. It looked like it was a fairly simple attachment. Is that realistic?
It's not a million miles from what it's going to do, in the sense that that's a mechanism that extends. It's like a robotic mechanism with a magnet on it. And the docking plate on the prepared client will be a ferromagnetic material with a set of markers, so the navigation cameras can see the markers, they can work out the position, and then literally it's going to magnetically capture it and stick on.
It does sound like you're slightly cheating, because you need the thing you're catching to have a magnet. Now that's fine here, but that won't always be the case.
So what we're lobbying for is that these big constellations going up, like OneWeb and SpaceX with the Starlinks, have a docking plate attached to them, so some mechanism that will allow a servicer to come up and dock with them and deorbit them safely as part of responsible space use. The other question we've got, of course, is the stuff that's already up there is non-ferrous, the upper stage rocket bodies. Well, we need something else, so we need a more complex robotic arm capture mechanism, because they really do have to grab on and take it out.
So we've been talking about grabbing them and deorbiting them, bringing them back to Earth or burning them up. But presumably you could do repairs, I guess, or maybe some other things.
Absolutely. I mean, so our colleagues in the United States and Israel with Astroscale are looking at life extension services. So that's going up. You're still docking with the satellite, but you're either providing more fuel or you're providing a second set of engines. And indeed, there are other companies who are also working on this technology.
Well, it's important stuff. We'll wish you luck, and we'll come back and find out how you got on.
Britain's space industry is booming. And because of this, big infrastructure projects are underway. Now I'm taking Chris to see the soon-to-be-completed STFC National Satellite Test Facility. You are some of the first people in the world to see inside, because before now, it's never been on television. So this is it. So it's amazing, although it's a building site outside, this is actually the test facility.
It's impressively large, isn't it?
Actually, that's what, the ceiling height.
Yes.
But there's nothing else like this in the UK. And so some of those big satellites that usually have to go abroad can now be brought here.
It's the size of the doors gives you an idea of how big the satellites might be.
Yeah, but what mind boggles me is this is all going to be a clean room. So, you know, you're not donning all the clothes, but on this scale.
It's impressive, isn't it?
Equally impressive is the huge vacuum chamber, 7 meters wide and 12 meters long. I feel truly dwarfed by this. Fully assembled, whole large satellites can endure the conditions of space before being wheeled around the corner to be subjected to the rigors of the launch pad. This is where they do the vibration tests, which is pretty critical for a satellite.
See, I've never built a satellite, but this must be terrifying when you do this with something you've built.
Well, yeah, you do it gradually. So you sort of do it on the subcomponents and you build it up to component level and then build it up to satellite level, which will be this. But yes, it is a bit terrifying because if you've got a satellite, I mean, you're talking about a few tons,
right,
which you're jiggling up and down quite violently. So this is one of my favourites because it's just the scale of it. This is the electromagnetic compatibility chamber.
It's a big metal box.
It is.
Why is it a big metal box?
Well, it's a Faraday cage.
Okay.
So you don't get sort of signals leaking out, you don't get signals leaking in.
So you can isolate the satellite.
Yes, and that's really important for things like antennas, because you want to test their profile and see how they work. What I find amazing is all these different test stations together in one building. Often you might get one of these in one location and then maybe a vacuum chamber in another. But having all this on one site and all on one level, that's the strength of this. And I think that's what the UK space industry was calling out for, and it's been delivered. So UK space just keeps on going from strength to strength.
Well, we'll have to see what comes through here. I hope maybe we get some astronomical telescopes in.
Oh, definitely, I think.
Yeah, for sure.
But yeah, I think it's definitely a success story, and the success story goes on. Britain is great at making spacecraft and now has world-class test facilities. And there's a chance that the UK might soon have its own launch facilities too. Plans are in place for sites from Cornwall to the Shetland Islands.
Next month, in a special hour-long edition of the programme, we'll be diving into the archives to look at how the Sky at Night and the BBC have covered the search for alien life. There's sure to be a few surprises.
But that we would definitely classify as UFO. He'll come back, Patrick.
Yes, he will.
He will come back.
I think, with a great respect, I think he was a satellite.
We do hope you can join us for that. In the meantime, from here at the new National Satellite Test Facility, good night.
Exploring questions about life, the universe, and our place within it. Reach for the Stars with Brian Cox and Adventures in Space and Time, streaming now on BBC iPlayer. And later on BBC 4, Revelations and Surprises from the Mission to Saturn. Goodbye Cassini with Horizon at 11:30.